So hi everyone, thank you Peter and the other organizers for giving me this nice opportunity to present my work. So today I'm going to present EFBV, which is a new algorithm for distributed optimization with compressed communication. This is joint work with Peter and Kai, who is a PhD student in our group. And the paper has been accepted at New RIPS, so we are going to present it very soon, two weeks from now. So yeah, we are looking, the three of us will be there, and we are looking forward to meeting you guys if you go to New RIPS. We get rid of this pointer, this. So here is the full title of the paper. So EFBV is, as Peter said, a unified framework which bridges the gap between two frameworks which were so far distinct, namely variance reduction, which works with unbiased compressors, so like in the Diana algorithm on one end, and on the other end, error feedback, also called error compensation, which works with the more general class of possibly biased compressors. So we consider this a distributed setting in which we have n workers or clients or nodes doing computations in parallel and communicating with a master or server. And we are particularly interested in federated learning, which is this modern paradigm in which a huge number of users are involved in a learning task in a collaborative way. So they do so by doing computations locally on their devices, like smartphones, based on their local private data, which are stored locally on their devices. So doing computations locally and communicating back and forth with distant servers that can be some service in the cloud. So I'm not going to give more details about federated learning because you're obviously familiar with it and certainly more experts than I am. So from my point of view, this is so mathematically we formulate the problem as empirical risk minimization. So we consider this optimization problem, which consists in finding a vector x in RD. So D is the dimension of this model X. D can be very large. So vector X minimizing an average of functions, Fi, which are supposed to be smooth with constant L, Lipschitz constant L. And there can be an additional regularizer R, which is not necessarily smooth. So we will use its proximity operator defined here. So in this, in the results which I show in the paper, the functions are convex, but in the paper we also have results in the non-convex but smooth case. So in our distributed settings, clients will compute the gradients of the smooth functions in parallel, and the master will be in charge of applying the proximity operator of the regularizer if there is any. So I've put different colors to emphasize that we consider the heterogeneous setting. That is, the functions Fi can be arbitrarily different, and there is no notion of similarity between these functions, the individual costs of the users. So there is no assumption of similarity whatsoever. So functions can be arbitrary, smooth functions. So we also define F, the average of the functions Fi here. And F in the results which I present is supposed to be strongly convex with constant mu. And the convergence speed, so I will present linear convergence results with the convergence speed depending on the condition number of F, which is this ratio of L, the Lipschitz constant, divided by mu, the strong convexity parameter. But again, we also have a result in the non-convex case in the paper. So to solve this optimization problem, there is a classical proximal gradient descent algorithm shown here, which is iterative at iteration number t. The gradients are all the gradients of Fi are computed, they are average. There is a gradient descent step, and then the proximity operator is applied, and this yields xt plus 1, the estimate for the next iteration. So this iteration is of course classical and very well understood. If gamma is chosen in this range, for instance, and you have linear convergence to a solution X star, which exists and is unique because we assume the function f to be strongly convex. So we have linear convergence, which means that this distance between xt, the estimate, and the solution X star is reduced by a constant factor 1 minus gamma mu at every iteration. So in our distributed setting, proximal gradient descent is implemented in this way. So at iteration number t, xt is first broadcast by the master to all clients, which compute the gradients of their individual functions in parallel. And these gradient vectors are sent to the master, which averages them, performs the gradient descent step, and then applies the proximity operator. And the bottleneck in this framework is communication, which is typically slow and costly. Okay, so the communication of these vectors, these gradient vectors, which are vectors in order d is the dimension which is large, and which happens for the baseline algorithm of proximal gradient descent at every iteration. So at every iteration, we have in this algorithm communication of these d-dimensional vectors, which is problematic. So the goal is to really to address this challenge of reducing the amount of communicated information, and for this, in this work, we consider the strategy of compressing these vectors. So in this talk, I will present 3 algorithms: Diana, EF21, and the new algorithm EFB. So we will not compress the gradient vectors themselves, but actually the differences between them and control variates, HIT, which are introduced and maintained by the clients. So these are these differences between the gradients and the control variates, which are compressed by applying these compression operators, CIT. And this difference, these compressed difference vectors, the DIT, or the vectors which are sent to the master. So the reason why we compress these differences is because we compress vectors that will converge to 0 along the iterations. Okay, because the control variates, like the gradients, they will both converge to the gradient of fi at x star. So the difference will vanish, and we will compress vectors which tend more and more to 0. And this will be the key to have an algorithm which is variance reduced, which means that it will converge to the exact solution.
Sorry, what is H? What is H? HN.
HN, so we have HIT, these vectors HIT, which are control variates. So there are vectors in RD, which are, so each client number I has this vector, this control variate HIT, which is used, so at the iteration number T, the client first computes the gradient of Fi at xt. It takes the difference with its local, its private control variate, and this is this difference which is compressed. Is it clear?
Well, I guess the question is, you didn't say how the H's get updated, right? So at the moment that this is mysterious.
Sorry, how the H is?
So I guess what's mysterious is that it's not clear from this how the H's change, right?
Ah, so, oh yeah.
So H is
yeah,
mysterious
so
at this point.
This will, this will be shown when I will show the actual algorithms. Yes, there is a, in addition to that, so yes, the process will be like this. So we compress, so the workers compress these differences. These difference vectors DIT are sent to the master. The master averages them. Then it adds back HT. So HT is the average of the HIT. HT is a control variate which is owned and updated by the master. Okay, so by adding this average difference to HT, this builds GT, which is the gradient estimate, which is used in the gradient descent step. And then the master applies the proximity operator. Okay, so this is the mechanism, the main mechanism. And in addition, yeah, behind the scenes, there is also the update, the way, the mechanism to update this control variates. Yes, that's true.
So Laurent, I have to say I like the slide because it shows that the Earth is rotating and the master is moving on the surface of the Earth as the communication happens, right? First it was up there, then it moved a little bit down. So this is a very kind of physically correct way of showing. Yeah, sorry for that silly joke.
Yeah, no problem. So yeah, then don't hesitate to interrupt me if you have any comment or question. I will be glad to take them during the talk. Any other question? All right. So the first algorithm of this kind, so which proceeds in this way, which I just showed on the previous slide, is Diana, which was proposed in 2019. And it has been then extended in several ways. I'm just mentioning here our paper, Murana, where Diana is presented as well as other algorithm under a unified umbrella, and we have several extensions. So Diana is expressed in a general way, using, for instance, bidirectional compression and also partial participation. So Diana is shown here. So it proceeds as I just said. So we have this the difference between, so at every iteration T for the clients in parallel. So the gradient vector is computed. There is a difference between the gradient and the control variate HIT, which is taken and compressed. And this is this compressed vector DIT, which is sent to the master. And we see now, in addition, this update of the control variate, which is a simple linear combination. So the update of the control variate just consists in taking the previous value and adding this vector difference vector DIT scaled by lambda. So there are two parameters: gamma, the step size used in the gradient descent step, and also lambda, which is used to update the control variates. So the two step sizes, gamma here in the gradient descent and lambda here. And the master updates also its own average control variates, HT, in the same way. Okay, so this is because they use the same lambda, they are kept synchronized in the sense that HT is always the average of the HIT owned by the workers. Any question on the algorithm? And Diana was proposed for unbiased compressors. So this CIT, the compression operators, which are applied to the vectors, they are random and unbiased, which means that the expectation of the compressed version of V is equal to V, whatever V. Okay, and these compressors must be random somehow, in the sense that an unbiased deterministic compressor can only be the identity, so which means there is no compression. So for unbiased compressors, yes, somehow are meaningful when they are random. So Diana uses stochastic or random unbiased compressors. So some examples of unbiased compressors, which are popular, are round K. So round K takes K elements chosen uniformly at random of the vector. So here, the dimension D is 5 and K equals 2. So 2 elements of the vector are chosen. They are kept and scaled by 5 over 2, D over K. So this is to maintain the unbiasedness property. And the other elements are set to 0. So this is a compressed vector here on the right. So in practice, only these K non-zero elements are sent. So the worker sends K real numbers, K floats, instead of D, with K which can be as small as 1. And we also typically also send the locations of the indexes of these k elements, which is a priori not known by the server, so which requires k log d additional bits to send these indexes, but it's a small overhead. So the compression factor is essentially d over k. And the second example is quantization, which can be applied on top of round k, for instance. So quantization consists in representing the real numbers using less bits. So typically a real number is represented as a float using 32 or even 64 bits. But we can quantize them to represent them using less bits. So here is a natural compression, which is shown. So every real number is approximated using an integer or a positive or negative power of 2, like these quantization steps here. So for instance, 1.2 would be represented either by 1 or 2 randomly, with probabilities which are chosen in this way to make the process unbiased. So in average, 1.2, yeah, we send either 1 or 2, but in average, this gives an expectation 1.2. All right, so these are two examples of popular random unbiased compressors. And I refer you to our paper on the trade-offs between compression error, dimension, number of bits. So we have analyzed the optimal trade-offs that can be achieved in this paper. So unbiased compressors are characterized by one value, one parameter, which is omega, which is the variance. So we suppose that there is this value omega, which is non-negative, such that the expected error, so the square norm of the difference between the compressed vector and the original vector, is less than omega times the square norm of the vector. So this assumption is not restrictive. It is satisfied for a large class of unbiased compressors, in particular for these two examples which I mentioned. It satisfies this assumption with the value of omega given here. So for round k, omega is d over k minus 1. So if k equals d, there is no compression. We send all the elements of the vector. So then omega is 0. Omega is equals 0 means there is no compression, and omega can be, so if k is equal to 1, which is the maximum amount of compression we can apply, just sending one real number instead of the d-dimensional vector, so then omega is equal to d minus 1. So omega can be arbitrarily large. And for quantization, it's this small value of omega equals 1.1 divided by 8, which means that essentially that we can always apply quantization for free, almost free. So it's a good idea to quantize the real numbers, which is intuitive. When we have an iterative algorithm, we don't need all these digits after the decimal point in all the elements of the vectors which are updated. So in addition, we introduce another value, omega average, here shown in pink. So we have this variance omega in green, and we have omega average in pink, which characterizes the variance after averaging the compressed vectors. So this is once we take the average of the compressed vectors, how much compression error remains at the end. And this is a key why random compressors are good. It's because this value of omega average is typically much smaller than omega. So it's not an additional assumption that we make on the compressors, because this inequality here is always satisfied for omega average equals omega. But typically, we are often able to exhibit a value of omega average, which is much smaller than omega, and which will, so the convergence speed will actually depend on omega average, not omega. And that is why it's good to have random compressors and a large N. So in particular, if the compressors are stochastically independent, then omega average is omega divided by n. So even if omega is very large, like with rand 1, where omega was d minus 1, if n is large, omega average can be very small. So this is the crucial property why randomized algorithm and here random stochastic compressors are effective in practice. So here is the main theorem of Diana. So if we choose lambda, lambda is a scaling parameter used to update the control variate. So we choose lambda equals 1 over 1 plus omega. Omega is the variance, so individual marginal variance of the compressors. And gamma, the step size for the gradient descent in this range, which depends not on omega, this is important, but on omega average, which is typically much smaller. So it's omega divided by n if the compressor is independent. Then this Lyapunov function, which is the sum of the square norm between the model error and the error on the square distance between the control variates and their optimal solution. So this Lyapunov function converges linearly. So we have this rate here, the contraction factor of the Lyapunov function, which is a maximum of 2 terms, 1 minus gamma mu, so which is basically the contraction factor on model estimate xt, and there is this additional term. So the second term comes from the update of the control variates. So what this means is that Diana achieves epsilon accuracy. So this Lyapunov function decreases to epsilon with a number of iterations proportional asymptotically to this value. And for instance, if n is large and we use rand 1, so rand k with k equals 1. So we communicate only one float at every iteration instead of d. The communication complexity measured in the total number of floats communicated to achieve epsilon accuracy. So it's reduced from d times L over mu. So d is the dimension which can be large. L over mu is the conditioning number, which can be very large as well. So d times L over mu is the complexity for the baseline gradient descent algorithm, so when there is no compression. And here the communication complexity is reduced from this product of these very large numbers to their sum. So the speed up can be very large using Diana with rand 1 compressors if the dimensions, number of n, not the dimensions, number n of clients is large. Okay, so that is why Diana is a very good algorithm. It reduces the complexity from d times kappa, the conditioning number, to the sum of d and kappa. Any question on Diana? So in that case, let me switch to the second algorithm, which is the EF21. So EF21 is also an algorithm which uses compression during communication, and which was proposed by Peter and co-authors last year. So the algorithm is named EF21, which means there are feedback in the year 2021. So EF21 is shown here. It proceeds in a similar way as Diana. So we also have this differences which are compressed, sent to the master. There is an update of the control variates HIT, and the master aggregates, forms a gradient estimates, and applies the gradient descent step and the proximity operator. So it looks very similar to Diana, actually. And I will come back to this important point in the next slides. And the main feature of EF21, why it's a good algorithm, it's because it works with any compressor, so possibly biased compressor, so with a larger class of compressors than Diana. Diana only works with unbiased compressors, and EF21 works with possibly biased compressors like Top K. So Top K is a popular compressor, which keeps the k largest k elements of the vector with largest amplitude, and sets the other one to 0. So this compressor top k is deterministic. There is no randomness here. We just select the k largest value. So it's deterministic, and it is obviously biased because there is a shrinkage towards 0. So top k is a deterministic biased compressor, unlike round k, which was random and unbiased. So such possibly biased compressors can be characterized using a value called alpha here, which also characterizes the expectation if the compressor is randomized or random, which is not the case of top k, but we can imagine random compressors. So this is again the expected square norm, expected compression error, so square norm of the difference between the compressed vector and the initial vector. So this error should be less than 1 minus alpha, for some alpha between 0 and 1, times the square norm of v. So this factor is less than 1 because alpha is strictly positive. That's why such compressors are sometimes called contractive. Okay, so because we have this contraction factor here less than 1. And we must have this contraction factor less than 1. Otherwise, we could allow for the compressor which always returns 0. Okay, so if you take the compressor which always returns 0, you have the expected error, which is equal to square norm of v, because this is 0 minus v, so this is v less than 1 times v. So in that case, if this factor could be 1, this would allow for this very aggressive compressor which always sends 0. But if we always send 0, we never communicate any information. There is no way that an algorithm could be proved to converge under this assumption. So this factor here must be less than 1. So this will be sufficient to get convergence, even linear convergence, but it's also necessary in this sense. So this assumption is tight. So top k satisfies this contraction assumption with the value of alpha given here, k divided by d. So in this mechanism called error feedback, the HIT, the vectors HIT, are not viewed as control variates. They are viewed instead as accumulation vectors of the past errors. So the mechanism works in this way. So we also compress the difference between HIT and the gradient. And then we update this accumulated error, HIT plus 1, as the previous accumulated error plus the new error which was made at this iteration. And this accumulated error, HIT plus 1, will be fed back to the compressor in the next iteration. That's why it's called error feedback. So it's a feedback loop. And it works because of this simple contraction property. So if we look at the difference, the compression error, so the error between the new updated accumulated error HIT plus 1 and the current gradient, then just by replacing its expression here and using the contraction property, we get that this error is now 1 minus alpha, which is less than 1, times the previous error between HIT, the previous estimate, and the gradient. Okay, so this feedback loop is stable and even contractive, converges. It converges because of this contraction property of the compressors. So here is the main theorem of showing convergence of EF21. So if we choose gamma in this range, which depends on alpha, so if alpha is small, no, if alpha is large, yeah, if alpha is large, there is more compression. Then gamma, the step size should be chosen smaller. So we have again, so under this assumption, we have again linear convergence of this Lyapunov function. And you can see that this Lyapunov function is different from the one in Diana. So it's actually very different, which shows that there is a completely different analysis of EF21 in comparison with Diana. So now the Lyapunov function is made from the objective function. So there is an objective gap here, plus the difference not between the control variate and its optimal value, but between the accumulated error, HIT, and the true gradient. So this Lyapunov function is shown to decrease linearly with this factor, which is again the maximum of two terms, 1 minus gamma mu, the contraction factor of on the model estimate, and 1 minus alpha 2, alpha divided by 2, which controls the contraction mechanism on the accumulated errors, HIT, so control variance. And the main point to observe here is that this theorem, this contraction factor, so the rate, the convergence rate, does not depend on n. There is nowhere n here. It only depends on alpha, which is the individual contraction factor of every compressor, but there is no notion of n entering into play here in this analysis. So let me show you the two algorithms, Diana and EF21, next to each other. So now we see that they perform the same steps, but there is only one difference, which is that there is this scaling parameter lambda here in Diana, which was chosen as 1 divided by 1 plus omega. So lambda appears in the update of the control variate here. So there is this scaling in green, whereas there is no scaling in EF21. Okay, so the lambda appears here in front of the differences DIT. So these difference vectors are scaled, but not in the construction, not in pink here, in the construction of the gradient estimate, which is used in the gradient descent step. So we see that actually the only difference between the two algorithms is just one scalar value, this value lambda. And even more intriguing is the following fact. It is that if we take an unbiased compressor, the kind of which we use in Diana, so it's characterized by its variance omega. So if we take such an unbiased compressor and we scale it, so we multiply it by lambda, with lambda equals 1 over 1 plus omega, then we obtain, so we make a change of variable, we obtain a scaled compressor C prime, which is now biased, okay, because we have scaled the unbiased compressor by this factor less than 1. So now it's biased. And this new compressor C prime, which is the scaled compressor, can be shown to satisfy the contraction properties, which we need to use C prime in EF21. So we can use the scale compressor C prime in EF21, and we have this value of alpha, which is 1 over 1 plus omega. So if we take an unbiased compressor, the kind of which we would use in Diana, and we scale it, we can use it in EF21. So now we could wonder, for unbiased compressor, is Diana just a particular case of EF21? Because now we see that we multiply the differences by lambda, so which is like scaling the compressor. So we could put the lambda here. Okay, then we would have the differences obtained by applying the scaled compressor to these differences. So would it be EF21? So yes, then these steps become identical, but not here, because there is no lambda here. So there is a scaling lambda here, but not here, not in the construction of the gradient estimate, which is unbiased in Diana. Okay, so there is still a difference, as we see. So they are very similar, but there is still some difference. The two algorithms are not equivalent, even for unbiased compressors. So now let me present the new algorithm, EFBV, which is shown here. So it looks like the two previous algorithms, but we have a new scaling parameter, new, which is shown here in pink. So we have lambda in green, like in Diana, and the additional scaling parameter in front of D, but in the construction of the gradient estimate, shown in pink here. And so if nu equals 1, and we use unbiased compressors, then this is just Diana. So Diana is a particular case of EFBV with nu equals 1 and unbiased compressors. And on the other end, if we choose nu equals lambda equals 1, so there is no scaling, and the compressors are contractive in the first place, so that satisfies this contraction property with the factor 1 minus alpha, then it's EF21. So Diana and EF21 are two particular cases of EFBV. And to go beyond these two particular cases and have an algorithm that works with more general, under more general assumptions, so we use the following idea of decomposing the compression error for any compressor into, so we decompose this error into two terms, its bias and its variance. So now we can characterize an arbitrary compressor using two parameters, its bias eta and its variance omega. So the bias eta is between 0 and 1. It cannot be 1, again, for the same reason as I mentioned. So otherwise, this would allow for the compressors that always return 0. So it would have a bias of 1, and we could not prove convergence of the algorithm under this assumption. So the fact that the bias is constrained to be less than 1 will be sufficient, but it's also necessary in this sense. And the variance can be arbitrarily large. Okay, so if the bias is 0, the compressor is unbiased. And if the variance is 0, the compressor is deterministic, like top K. Okay, so we have these two parameters, the bias and the variance. Any question? No?
Yeah, I think it's important to pause here a little bit more because
Sure.
This is something which appears first in this paper, this kind of a new definition of a parametric class of compressors with two parameters in departure of all previous works. So maybe it makes sense to just pause here and have some discussion.
Yes. Yes, so EFBV, the name EFBV comes, so it means error feedback with bias variance decomposition. So it's captured here in this expression, but yeah, it's true. You're right, Peter, to say that we brainstorm quite a bit before we arrive at this conclusion that this is the right way of characterizing compressors.
Excuse me, Professor?
Yes?
I have a question. Well, because these three algorithms are too similar for me. So from EF21 to EFBV, it's like adding a new insight. But intuitively, I couldn't see the benefit of adding this new here. So can you explain it?
So yeah, let me show again Diana and F21. So as we said, in Diana uses unbiased compressors, but there is this scaling parameter lambda to tame the random error. This lambda is not needed in F21 because in F21 the compressors are contractive already, whereas in Diana there are the compressors are more raw in some sense, because they can have a variance which is arbitrarily large. So somehow, yes, this idea of scaling the error is natural, because in Diana, the compression error otherwise would be arbitrarily large. So that's why we need to multiply it by this constant here. So in Diana, there is this lambda which appears here, but not in EF21. So in EFBV, we introduce now this, so we still have this lambda parameter because we want to allow arbitrary compressors which are not contractive in the first place, like unbiased compressors with variance omega, which can be very large, or not contractive before scaling. So that's why there is this lambda, but there is an additional nu, which will also be between 0 and 1. So in Diana, nu equals 1, it's because the gradient estimate is unbiased. So this is important in the theory. So to develop the Lyapunov analysis, we need this unbiasedness to be able to characterize the squared difference between xt and x star. So nu equals 1. But in the new algorithm, yeah, we will have a biased estimate of the gradient. So there is this nu. And nu will be also used, just like lambda, to mitigate the effect of the errors. But now it's on, so this is an error on dt. dt is the average of the received compressed vectors. So dt is the average of the dit. So we have a compression error after aggregation, after averaging. So after averaging, there remains some error, which we have to mitigate. But this error is typically much less than the error in the individual compressors. So nu is needed, but it will be typically larger than lambda.
So if you allow me, I could
Sure.
try to say something in a very, very different way. Give some insight. So one way to think about these methods is the following: that the literature on error feedback and the literature on variance reduction for unbiased compressors are two separate pieces of literature. They have their own algorithms, their own proof techniques, and so on. But both clearly deal with very similar problem: distributed optimization with communication compression. But error feedback is a very different mechanism for dealing with communication compression. It is then let's say Diana for dealing with unbiased communication compression. However, as Laurent wrote these two methods side by side, they start looking similar, EF21 and Diana. But however, this is because error feedback before the EF21 method was invented looked very different. And then if you put error feedback original one, not error feedback 21, side by side with Diana, this would look very, very different methods. However, the original error feedback mechanism, which was invented in 2014, has many issues which were resolved in this EF21 paper. And as soon as we found out that, in fact, you can, in some sense, replace the original error feedback by error feedback 21, and you even get a better method in practice and definitely better in theory, then suddenly the similarity emerged. And somehow the starting point of Laurent's discussion here is that we now had this new breed of error feedback, which we call error feedback 21, which is better in theory than the original one. And now for the first time, we see similarity to the previous mechanism. So we can ask questions of the type, is this superficial similarity? Why there's just such a small difference? Can there be maybe more general analysis? What does this all mean? Okay, and really this research here is born out of these questions. So I'm not answering the question about this particular parameter, but I wanted to give a broader insight into what's going on here.
The key will be to exploit. So because Diana relies on randomness, and EF21 is somehow blind to randomness. But what matters in EF21 is this contraction factor alpha, which can come from different sources. Like in top case, there is no randomness. So it's just a shrinkage. So sparsification, which yields this contraction which we need. But another way is to take an unbiased compressor and to scale it, and this makes it contractive. So the contraction factor, can come from in different ways, but scaling is one way to get it, and this is what matters in EF21. But we want to go to a finer characterization of the mechanism in EFBV to exploit randomness, just like in Diana. And for this, this is a reason why we need these two parameters, lambda and nu, which can be different.
Thank you, Professor. I think I get the point.
Yeah, it's clear now. Did it answer your question?
I think I get the point, but I will read more later.
Yeah, you can ask again if it's still not clear. So I was here saying that arbitrary compressors are now characterized by their bias and their variance. And we also define the third value, omega average, which characterizes the randomness or the variance after averaging the compressed vectors. So this is a square norm of the difference between the averaged compressed vectors and their expectation. So this is a variance after averaging. So it's not an additional assumption. Again, this inequality is satisfied with omega average equals omega, but we can often exhibit a value of omega average which is smaller than omega. And this is the key, just like in Diana, to show, so to exploit the randomness in EFBV. So if we have if we take a compressor, we are characterized by its bias and variance, then there exists, we can scale it. So we can generalize the scaling mechanisms, which I have briefly mentioned for unbiased compressors. So, but for arbitrary compressors, we can scale them in such a way that the scale compressor C prime becomes contractive. Okay, because this contraction properties, which is what we need in EF21, and actually also in Diana, in the sense that this lambda equals 1 over 1 plus omega is the scaling which makes the scaled compressor contractive as well. So in the two algorithms, all algorithm actually, we somehow need this contraction property, which is behind the scene and which makes the algorithm contractive, so converge linearly. Okay, so if we scale, so there exists a scaling parameter such that the scale parameter, the scale compressor becomes contractive, and we have this value of alpha, which depends on the bias and the variance. And the best, yes?
Yeah, excuse me. Yeah, one question. So, do we assume for the compressor in EFBV algorithm any sort of an unbiasedness? So, is it an unbiased compressor in
No, it's
EFBV?
any compressor with a bias. So if it's unbiased, eta the bias is equal to 0. So the compressor is any compressor which satisfies these two assumptions. Okay, so it must have a bias less than 1, and it can have an arbitrary variance.
Oh, okay, got it. Thanks.
Okay, so it can be unbiased if eta equals 0. It can be, so like around k. It can be deterministic if omega equals 0, but it can be random and biased, for instance. Or so this class of compressors is more general than the unbiased compressors, and it's also more general than the contractive compressors. So it's indeed a larger, strictly larger class of compressors which we allow here in EFBV.
Yes, and I wish to add to this that so in some way, one way to think of this is that this is larger class, but another way to think of it is that this is better parameterization of compressors than the usual parameterization. Now let me explain very briefly why. So if you assume that, let's say, you have a contractive compressor, then you know that it's contractive, but then it's not enough information to go by for you to do good theory, because too much is lost by summarizing the whole compressor into one number. Too much is lost. And in particular, you lose information about the randomness hidden inside, and you cannot get any benefit from the randomness. Okay, so if you have, let's say, a random K compressor and top K compressor, random K after scaling has the same alpha as the top K, and from kind of EF or EF21 type of theory, they are indistinguishable. But the random one should benefit from the variance being divided by the number of clients, but it will not in EF or EF21 type theory, because somehow that information is lost. But here, since we work with any class of compressors, like any mapping, and we do the natural bias variance decomposition. And this natural decomposition leads to a parameterization of compressors using two numbers. And it turns out these two numbers already are much more informative than just a single numbers. Somehow knowing these two numbers can tell you maybe how much randomness there is, how much exactly there's bias, and so on and so forth. And then you can benefit also from that extra information.
Any other question?
Не хватает Димаса доставщика, конечно.
So I don't know what this was. Was this Igor?
Yes. Do you have a question, Igor? Not in Russian?
Maybe he was speaking to somebody else.
All right. So yeah, exactly. Yeah, Peter summarized the point very well. So indeed, yeah, we have more information in the two values eta and omega, the bias and the variance, than just in the contraction factor alpha. So to make scaling the compressor in such a way that it becomes contractive is the property which is needed to make the algorithm converge. But the way to choose this scaling parameter can be now tuned more finely than just because we have these two scaling parameters, lambda and also nu. By choosing them differently, we can exploit the randomness which is of the individual compressors and the randomness which remains after aggregation. All right, so the optimal scaling parameter, which makes this contraction factor 1 minus alpha minimum, is given here. Okay, so it depends on both eta and omega. And we'll cover the properties that we have seen before, that for unbiased compressor, so if eta equals 0, the optimal scaling parameter is 1 over 1 plus omega, which we used already in Diana. So we will use EFBV with these optimal values of the scaling parameters, which have this closed form, which we just described to make the compressors contractive. So we have this optimal value of lambda, which is given here. And the optimal value of nu is has the same form, but now with omega average instead of omega. And the key is that omega average is typically much smaller if n is large than omega. So if n is the number of clients and is large, omega average with independent compressors is equal to omega divided by n. So omega average is much smaller when n is large, which means that in turn nu is larger than lambda. So we have a larger scaling in EFBV than in EF21. So in EF21, we have nu equals lambda. So we ignore this property of the randomness being decreased by aggregation, because the randomness has disappeared from the analysis too early in the process. We just reason with respect to alpha. So omega average equals omega in EF21. We ignore the randomness properties. And in EFBV, nu is chosen larger than lambda, which means that the gradient estimate it's constructed in such a way which is less conservative. So EF21 is too conservative. It takes a too small step size here in the construction of the gradient estimate. Okay, so EFBV somehow takes a larger gradient steps than EF21. That's why it converges faster, possibly. So here is the main theorem. Should I hurry up? So are we good with the time? I've not.
So that's fine. So extra few minutes, completely fine.
Okay, yeah.
And we only have 3 more slides, so that's.
I will conclude just after this slide. So yeah, okay. So here is the main theorem. So we have for gamma chosen in this range, we have a linear convergence of EFBV, with the Lyapunov function, which is similar as the one of EF21. So as Peter said, we can see EFBV as a refined analysis of EF21. So we have a similar Lyapunov function, which decreases linearly with this factor, which is again the maximum of two terms, the contraction factor on the model and the contraction factor on the control variate. But the key is that now the step size can be chosen larger, because it depends on this ratio between R average, the contraction factor of the synthetic aggregated compressed vector somehow, which is used in the construction of the gradient estimate. So R average contraction factor depends on omega average, which is typically much smaller than omega. And R is the individual contraction factor of the compressors. So this ratio, R average over R, can be small if N is large. That's why gamma can be chosen larger. So we allow for larger step sizes, and that's why the convergence can be faster. So now we have a convergence rate which improves with N, just like Diana, but unlike EF21. And the algorithm works with any compressor, not only unbiased compressors like in Diana. So we combine the benefits of the two approaches. Diana, which benefits from randomness and large N, but works for unbiased compressors, and EF21, which works with more general compressors. Here are some results. So there are more in the paper, but we see here the improvement of EFBV in comparison in blue, in comparison with EF21 in red. So it's in log scale, so we have some improvement. And here the compressor is a composition of top K and 1K, so which was chosen to be random and biased. So to conclude, EFBV is a new algorithm with a new analysis which unifies the two mechanisms, two approaches of variance reduction with unbiased compressors like in Diana, which was a state-of-the-art algorithm for this in this vein, in this philosophy, and EF21, the recently introduced state-of-the-art of error feedback, which uses arbitrary, possibly biased contractive compressors. So as I said, it combines the benefits of the two approaches, working with a large class of compressors, and also benefiting from having a randomness and a large number of clients. So for future work, there remain several questions. So using stochastic gradients instead of the true gradients. So currently in this analysis, we compute the true gradients, but this can be costly if the individual cost function Fi is also a finite sum of relying on a data set which is very large for the individual worker. So we could use stochastic gradients. We could also consider bidirectional compression, because here we focused on compressing the communication from the clients to the server, but we could also, there is also communication in the broadcast step. And a natural question is, of course, to design, now that we have this refined analysis, to imagine, to design new types, new examples, new design of compressors, which are random and biased, and which are optimal or in the sense of this analysis. Thank you for your attention, and I will be glad to take questions.
Yes, could you please go back to the theoretical results of EFBV? Yes, so could you please clarify at which point do we get the improvement with the increase of the number of workers?
So we get the increase, so from this ratio, R average divided by R. So R, because R average is smaller than R, because it relies on omega average, the variance, the average variance after averaging, after aggregation of the compressed vectors. So omega average so if the compressors are independent, is omega divided by N. So you can replace omega average by omega divided by n. So that's why when n is large, it tends to 0. So what remains is only the bias term.
Yeah, okay, thanks. It
So
clarifies.
there is a benefit if there is randomness. So you need some variance here, and also a large n. So there must be, if you take deterministic compressors like top k, then these terms disappear or 0. There is just the bias, and there is no. Then the algorithm recovers EF21. So for deterministic compressors, there is no advantage. So the analysis exploits randomness and benefits from having large n, because you have omega divided by n here.
Sorry, what is S in this theorem? S.
So is this S here?
Yes.
What is S? What is S? Maybe just a constant, no? Is it?
Probably it was
Yeah,
defined
maybe
previously.
I think I simplified the statement to make it on this slide, because in the paper, yes, there is this theta which is chosen here like this, but there is a S also which is hidden somewhere. But yeah, it's just a matter of constants, I think. So what matters is R average divided by R. Yeah. Theta, yeah, theta. Well, theta just appears in the formulation of the Lyapunov function. So yeah, we can ignore it somehow. It's just a constant. Yeah.
Thank you.
Any other question?
I see a question in the chat by Thomas. Maybe you can ask directly. If he's still here. Cannot activate micro. So I'll read the question, Laurent, for you. So Thomas Ortega is asking, thank you for the talk. Intuitively keeping track of the control variate is bad for global differential privacy. Is there any way to add noise to it and still ensure convergence?
So I'm not an expert of this privacy aspects. So I think when we consider stochastic gradient estimates instead of the true gradients, there is an additional source of error somehow, which would be good with respect to privacy. Is it correct, Peter? Yeah, can you comment, please, on this?
Well, the really true answer I could give is that I do not know. I didn't think about this question. I do not know how this would really interface with privacy. I didn't think of it. So I don't know whether adding noise to the control variates would resolve this or not. The control variates really are there to force convergence to the solution. And if we don't have them, we get convergence to some neighborhood. So one can not have the control variates, and there'll be some sort of convergence to some neighborhood, but then we lose on optimization. So
yeah.
whether at the same time we can get both, I'm not quite sure. Do we have any other questions?
Yeah, so also as far as I get, you provided on this slide the results for the strongly convex setting.
Yes.
However, do you have something covering convex setting without strong convexity? And
so the statements in the paper's analysis is weaker in the sense that we consider the Polyak-Lozakiewicz or even the KL Kurdika-Lozakiewicz assumption, which is weaker than strong convexity. So we can have non-convex functions, smooth non-convex. If they satisfy the KL properties, and we still have this linear convergence result here. So yeah, I just showed it as a strong convexity to simplify the notations, but yes, this is the first kind of results we have, and we also have results in the non-convex case, so with the Fi being smooth, but possibly non-convex. And then we have a sublinear convergence rate of 1/t on the square norm of the gradient.
Okay, are these results in the paper?
Yes, they're in the paper. I think it's so. Here is theorem 2 is shown, but I think theorem 3 is on the non-convex case.
Thanks.
Any other questions? Anyone? So Laurent, I will have a question. So this
I want.
Hello.
Hi, hello. Can you hear me? Hi, Laurent.
Yes.
I want to ask a question.
Oh, go ahead.
The Lyapunov function is defined with the function value.
Yes.
And the distance between the control variable to the gradient. I have an idea to, can you measure the distance to the optimal point?
So
I mean, the function value is replaced by the distance to the function to the optimal point, not the function value.
yes, that's a good question, because that would be, for instance, needed if we would consider more general setting. Instead of applying gradients, we could apply operators. So to solve monotone inclusions, for instance, or to go towards non-smooth functions. So you compressing the proximity operators of functions instead of gradients, for instance. So and the answer is that so no, yeah, I did not manage to get a result on the squared distance between xt and x star. Yes. So to show
this idea comes.
I need this Lyapunov function here, because yeah, it seems that it's very complicated, or even not possible to get any result for biased compressor. As soon as we go beyond, as soon as we remove unbiasedness, then the analysis seems to be intractable. Yes. So I did not manage to get anything using the square norm, the square distance with biased compressors.
Thank you.
Yeah, just one comment on this. Please note that the diagonal analysis has that distance squared to the solution. EF21 does not, and this kind of generalized result also does not.
Yes.
That's an open problem. Maybe somebody can deal with it somehow. We don't know. I did have a question, but I wish to give a chance to others to ask. My question is less important. So I'm going to ask it now, and this could be maybe the last question, since we already are a little bit over time. So the question would be, so this new definition of compressors, these, let's say BV compressors, or whatever we want to call them, these ones parameterized by two parameters. Do you see any other research directions which would involve these compressors? So not for this particular algorithm, but where else can we see maybe this type of a parametric class of compressors used and possibly shine? what other setup would you believe that could be useful?
So yeah, this is a good question. So in the Murana paper, we present Diana and Saga and SVRG as somehow being the same. So it's just that Diana is implemented on a parallel architecture, whereas Saga is for finite sum minimization, where we sample the gradients. But it's somehow the same philosophy. So now if we go to algorithm like Sarah and Paige, Marina, then they have a biased mechanism of building the stochastic gradient. So would this analysis be useful in this setting? Yes, this is a question.
I would have even simpler questions. So looking at DCGT, okay, assuming overparameterized or interpolation regime, and then getting maybe convergence to a neighborhood because of the bias. And if the bias happens to be not too large, one should get a linear rate and the strong convexity to some neighborhood depending on the bias. But this could be a very powerful competitor even to both of these methods. If the bias is maybe there but not too large, the interpolation regime will make sure that you don't need any Diana trick, right? And the small bias will ensure you get the accuracy that you need, so there'll be no need for any kind of error feedback or hopefully or Diana type of variance reduction, and it could be a possibly very good method in that regime.
And also, yeah, in decentralized optimization with varying networks. So you use a bias to capture the fact that the topology changes over the iterations, right? So could we benefit from this refined analysis here of the randomness and bias for this decentralized problem?
I'm not sure if we use bias in that case. We just use it's not about the changing topology, right? I mean, the bias is just because there is a topology and it's not fully connected network. It's already coming from that. You just get contractiveness just from the fact there is topology, not even changing, right? So okay, so what you're trying to say is that whether there is any usefulness for this in decentralized optimization, where maybe one can think of some different type of communication than contractive communication. So it would be maybe a richer BV communication pattern and potentially do something more interesting, right? That's a good question.
Yeah, I'm just brainstorming live, but yeah, there seems to be other settings in which this bias variance decomposition could be useful.
Okay, so all of this is protected by copyright, so none of you are allowed to write papers on this topic, okay? All right, well, thank you very much for the very nice talk. Thanks a lot for the discussion, everybody, and have a nice rest of the day.